Hello, everyone. It's a pleasure to have everyone here for one more day of our event. Today, I would like to introduce Professor David Anderson. He's professor at Ohio State University. He got his PhD at University of Michigan, and he was here in Brazil a couple years ago for a postdoc fellow in IMPA. So I think some of you know him. His works, his work in algebraic geometry and combinatorics, and today he's going to talk about Schubert polynomials. So it's with you.
Ok. Boa tarde para todos. É prazer de estar aqui com vocês. E obrigado, Jordan e Bernardo e todos para organizar. Desde agora vou falar em inglês. But it was a nice opportunity to remember my time in Brazil, which, as Claudio reminded me, was already 7 years ago now, more than a few years. I want to talk to you about a subject that's, I think, a little bit of a different flavor of Lie theory from most of this conference. So I'm going to keep it at a fairly high level of discourse. As Jordan said, it connects algebraic geometry with algebraic combinatorics, and Lie theory is involved. Let me talk about Schubert polynomials. So to start with, and I'd like to ask somebody to interrupt me if you have questions or if somehow the screen presentation is not working out. I had a little snafu with the iPad, so things are working a little differently. I want to start with a very old style of question. So this goes definitely back to the 19th century. If you've got a linear family of quadratic forms in n variables, how many of them have rank at most r? Okay, so what do I mean by that? Well, the quadratic form might be non-singular, or it might have a kernel. And more precisely, I can write down any quadratic form as an n by n matrix, which is symmetric, the standard way of polarizing a quadratic form. This can be a symmetric matrix. And each entry should be linear in some variables. And for now, I don't really care about how many variables. That's what it means to have a linear family. And well, another way of phrasing this question is, what is the degree of the locus where the rank of this matrix is at most r? So where r is some number between, say, 0 and n. Okay, this is just a rephrasing of this question. This is maybe how we would think of it now. And the original question is how people might have thought about 150 years ago. Well, this sort of becomes a question of algebraic geometry, and there was an answer given almost 150 years ago, and here's the answer. So it was given by Schubert, attributed to Schubert in a paper by Segre, and then kind of recast in a paper by Giambelli from 1911. There's this nice, wonderful ratio of factorials. You can reorganize it to a nice ratio of binomial coefficients if you like those better. As a little sanity check, if r is n minus 1, well, then the degree of the locus where rank of a matrix is at most r, you're just imposing that the determinant be 0. And the determinant is a degree n function if you've got an n by n matrix of linear functions. So that says if you plug in r equals n minus 1 to this formula, you get n, which is good. Conversely, if r is 0, that's just saying all of the entries are 0, and that's a linear subspace, right? If you make a bunch of linear forms equal to 0, that cuts out a linear subspace. And so its degree should be 1, because it's linear. So those are just kind of extreme cases of this formula, and the interesting stuff, of course, is what happens in between. This is sort of prehistory to everything I'm going to talk about, but I want to use it as an excuse to set up a different kind of problem, which is the one that I'm going to be focusing on. So here's another way you could set up this problem. You think of a symmetric matrix canonically as a map, a linear map, from a dual space to a space, where E is now just some n-dimensional vector space. So the canonical thing is to think of it mapping from the dual space to a vector space, and the dual is in there to remind you of that. Any n by n matrix would give you such a map. What's special about a symmetric matrix is that if you look at its graph, and by definition a graph is just take the take a vector and look at its image, so that's some n-dimensional subspace of this n plus n dimensional ambient vector space, then I think, as Enrique mentioned this morning, anytime you have a dual space summed with a space itself, it comes with a canonical symplectic form. And the fact is that the graph of a symmetric matrix is Lagrangian, and that's a complete characterization of symmetric matrices. So if you do this construction, form the graph, you get a Lagrangian subspace if and only if your original matrix was symmetric. Okay. What else can we say? Well, what's the kernel? You can read off the kernel of the matrix by intersecting the graph with a particular subspace. This is very elementary. You're just unfolding the definitions. What does it mean to be in both of these? Well, it means that you're looking at f comma a times f, but you're also looking at f comma 0. So this just says a times f is 0. A times f is 0 if and only if you're in this intersection of two subspaces. This is a Lagrangian subspace, the graph is, and this E star plus 0 turns out also to be a Lagrangian subspace with respect to this canonical symplectic form. Okay. Of course, the rank of a matrix is at most R if and only if its kernel has dimension at least n minus R. And now we've got a nice characterization of the kernel as the intersection of two Lagrangian subspaces. So the original problem, which is a problem about quadratic forms, turned into a problem about intersecting two Lagrangian subspaces of some space that comes with a symplectic form. And what the upshot of this is that the map associating a graph to a symmetric matrix defines for you an embedding of symmetric matrices in Lagrangian subspaces of this particular space. And this Lagrangian, so this LG stands for the Lagrangian Grassmannian, and it parameterizes all Lagrangian subspaces. And I've written here to start making the connection with Lie theory. By Witt's theorem, any Lagrangian subspace gets moved to any other one by an isometry of the symplectic form. So this way of unraveling that is that this Lagrangian Grassmannian is a homogeneous manifold with respect to the symplectic group, and the stabilizer of any particular subspace is some parabolic subgroup. So you can write it as sp2n mod p. It is a generalized Grassmannian in that sense. I guess I should mention this whole talk I'm thinking about things over the complex numbers, not over the real numbers, although this particular statement works just as well over any field. Okay, so the condition of intersecting, where I take any Lagrangian subspace and I intersect it with a particular one. So this defines and I impose the condition that the dimension be at most n minus r, or some number. That defines what's called a Schubert variety in the Lagrangian Grassmannian. LG is the Lagrangian Grassmannian. So what I mean is I'm taking all L's such that its intersection with this fixed space has dimension at least something. And Schubert varieties are defined this way. So kind of in broad terms, the original problem I've translated from something about imposing determinantal-like conditions on matrices to looking at certain subvarieties of this Lagrangian Grassmannian. And in particular, you can solve that problem of how many quadratic forms have at most rank R by computing the equivariant cohomology class of this particular Schubert variety in the Lagrangian Grassmannian. Okay, so let's see. But more generally, what is the class of a Schubert variety in, say, the Lagrangian Grassmannian or in kind of a more general Grassmannian altogether? So what I want to do for the rest of the talk is talk about this problem about finding the class of a Schubert variety. And most of the talk I'll actually talk about a different setting, a different ambient Grassmannian, but we'll come back to this one later. I want to tell you about what's been done and kind of where a little bit about the history of this problem, going back a little ways. So as I've tried to describe, these questions go back to 19th century enumerative geometry, and some of them go back even farther. Newton would have recognized some of these types of problems. But since their origins, the kind of techniques used and the communities who study them have bifurcated. And I'm just going to sketch out two forks, but there are many other applications here. So let me kind of sort of briefly and certainly by no means complete history of the subject. So the story started out where we started out in 19th century enumerative geometry, where people considered problems like the one I mentioned, how many matrices in a given family have rank at most R. And Cayley gave some of the original formulas of the type that we're looking at. Schubert was kind of the master of finding all kind of generalizations of these, and Giambelli refined those formulas later on. So this is roughly in chronological order. This subject developed into early algebraic topology, and some of the early algebraic topology in kind of the 20s and 30s was in some sense used to address this type of problem, like intersection theory and Schubert calculus. You know, Hilbert's, I never get the problems right, but the numbers right, but Hilbert's 15th problem that has to do with putting Schubert calculus on firm footing. And van der Waerden claimed to have done so by basically observing that Lefschetz's construction of homology groups and intersection products let you set up a formalism into which Schubert's enumerative calculus fits. Sorry about that. Put that away. So it's in this context, it's worth pointing out Erisman's work in the 30s. He wrote down a cell decomposition of the flag manifold and into what is now called Schubert cells. And the closures of Schubert cells are the Schubert varieties that we're talking about. Okay, so after that, again, I said this is a sort of rough and biased sketch, but there were two kind of branches that came off, and one is Borel's and others kind of theory of transformation groups. So people started looking at the way that groups act on the flag manifold. So the unitary group acts and the symplectic group acts and the orthogonal group acts. And they did this both in the topological category of Lie groups and in the algebraic category of algebraic groups. And so Chevrolet was involved in that as well. And that developed into, you might say, like this sort of group theoretic picture developed into Lie theoretic combinatorics by the 70s, 80s, and some of this branch continues in that vein now. So where one looks at a Lie group and looks at the Weil group and various kind of Lie theoretic constructions, and you try to look at things like reduced words for expressing a Weil group element as a product of simple transpositions, and see what that says about Schubert varieties and things that one is interested in there. For example, intermediate to that, Bernstein, Gelfand, Gelfand, and de Maizière introduced what are called the divided difference operators now. And this gives a way of computing Schubert classes. And I'll talk about that in more detail shortly. Okay, but also around the middle of the 20th century, kind of a mainstream algebraic geometry got interested in extensions of Giambelli's formula. And there's a kind of funny story where, you know, in the 60s, when people were looking at characteristic classes, Tom realized that if you look at a map of vector bundles, which you can think of as a family of matrices, of course, and you can ask, well, where does that map acquire singularities? In other words, where do those matrices drop rank? And it's exactly the analog of the problem that we considered at the beginning. Well, by looking at the cohomology rings of the Grassmannians, if you take big enough vector spaces, they just turn into polynomial rings. And so Tom realized that there must be some universal polynomial that that represents such a class. And Porteus, a few years later, wrote down that polynomial and proved that it is the one that Tom asked for. But I think probably, I'm only speculating, but probably unbeknownst to them at the time, this was actually Giambelli wrote it down, 60, 70 years earlier. Exactly Giambelli's formula for this rank locus. Okay, so that thread kind of developed in the 70s. Kempf and Laxov wrote down generalizations of that formula, and their formulas turned out to be interesting, and I'll mention something about them later. And these formulas have all been used in modern enumerative geometry. So Joe Harris and many of his collaborators in the 80s both proved new formulas and applied them to the geometry of Riemann surfaces, where one asks for special divisors on algebraic curves. Can you tell if they exist? Well, you can plug in their kind of the desired invariants to one of these formulas, the Kempf-Laxov or Tom Porteus Giambelli formula, and out will pop an answer. And so Harris and Eisenbud and various others used that to great effect in the 80s. And Fulton in the 90s kind of developed this further to answer more refined versions of these degree questions. So I've got a couple other names here, Lascaux and Schutzenberger and Billy and Heyman from the 80s and 90s. These are mostly from the combinatorial point of view, and this is where I'll be turning to next. The reason I wanted to bring this up is that there are bridges, there have been occasional bridges across this kind of transformation groups and sort of more mainstream classical algebraic geometry divide, but it's my opinion that more should be built. And especially given that there's lots and lots of Lie theoretic combinatorics out there, and there's been lots and lots of development in these kinds of questions about divisors on curves, and there still seem to be connections between these two, and occasionally we discover them, but I'm sure that we've missed a lot of them. So if you're interested in any of these kinds of things on either branch, or possibly on a third branch that I haven't sketched out here, then it'd be great to get more people involved in building bridges here. Okay, I'm gonna turn to some more a little bit more of a detailed setup, talking about Schubert varieties and flag varieties. So here's the but yeah, I'll say, like, please do interrupt me with questions at any time. So here's the general setup that we're working with. And shortly I'll specialize it to just a particular group. But in general, everything I'm saying works if you've got a semi-simple complex Lie group, G, with Weil group, W. You can take a Borel subgroup and an opposite Borel subgroup. That's what B minus means. They'll intersect in a torus, a maximal torus. The torus is just C star to the n for appropriate n. Then you get what's called the flag variety, and that's just the quotient space G mod B. And it's going to come with actions of all of these groups. So G is going to act on the left. We're modding out on the right. G will act on the left, as will all of these subgroups. Okay, so here's a definition. If I take any Weil group element, I can imagine it as an element of the group. Technically speaking, you have to choose a lift, but that choice of lift won't matter. So then I can look at this subset of the group, B minus WB. I can look at that mod B on the right as a subset of G mod B, and that will be what's called a Schubert cell, and the Schubert variety is what you get when you take that closure. So I don't know how well I can point here, but I suppose I can do a little markup. Right, so it's not a good color. White. Oh, sorry, I probably shouldn't have done that. Let's leave the markup alone. Gotten too used to my tablet and pencil. But. All right, so this is what a Schubert cell is. It's the closure, this is what a Schubert variety is. It's the closure of a Schubert cell in the flag variety. The Bruhat decomposition tells you that Schubert cells give you a topological cell decomposition of the flag variety for any group G. And then whenever you have a topological cell decomposition, the cohomology classes of their closures form a basis for the cohomology ring. And in fact, that's true for equivariant cohomology. So if you know what that is, then you probably know this statement. And if you don't, then I'm not going to teach you here, but it's true. Yeah, so the Schubert varieties, or their classes rather, form a basis for this ring. Now, Borel in the 1950s proved that you can write down a presentation for this ring, say with Q coefficients, rational coefficients, as a polynomial ring in some number of variables. The number, by the way, is the dimension of the torus, modulo some ideal. And he told us what the ideal is. It's some ideal of Weil group invariance. And his proof works for equivariant cohomology as well. So he shows that there's a similar presentation where you replace Q by whatever the equivariant cohomology is of point. This is some polynomial ring. And there's some kind of variation of the ideal. So where we're going to be going with this is we want to find a way of getting rid of this mod the ideal story here. We want to find actual polynomials that represent Schubert classes. And we'll do that in this context where G is a classical group. So mostly I'll be talking about SLN, that's type A, and a little bit about SP2N, we already saw that, that's type C. And there exist analogs in the orthogonal group cases, types B and D, but I won't tell you the details of those. The important point is all of these flag varieties come in series, depending on N. So let me tell you about them in a little more detail. So the type A flag variety just parameterizes all nested chains of subspaces where the dimension of each of the ith space is I. So F1 is contained in F2 all the way up to Fn. The Weil group in this context is the symmetric group. So it's just permutations of 1 through n. And there's a nicer, in my opinion, description of the Schubert variety. Rather than just as the closure of some orbits, you can write it down as defined by these kind of intersection conditions that we saw before. This is going to go by a little too fast to digest, but on the fly. But basically, I want you to think that there's some number that you can associate to any permutation matrix. I kind of sketched that out for you here. If you write down the permutation matrix for W, and you look at the lower left Q by P submatrix, then count the number of ones that you see in there, or equivalently, ask for the rank of that submatrix. That's that number. So there's some number that you can easily figure out, and here's a formula for it. I want to make sure that the pth subspace intersects the n minus qth standard subspace in that amount for all p and q. That's another description of the Schubert variety. Well, if you think about it a little bit, not too hard, then there's kind of natural embeddings of flag variety for all flags in Cn in the one for all flags in Cn plus 1, right? The nth component here is going to be just the standard Cn. You embed Cn and then Cn plus 1 and so forth, and that'll embed flags. And you can do this ad infinitum until you get the union of all of them, which you might call something like flags in C infinity. The corresponding thing to do in symmetric groups is just embed permutations of 1 through n in permutations of 1 through n plus 1, where you leave n plus 1 alone. Okay. And this computation, if you use Borel's computation of each one of these individual flag varieties, you see that the relations disappear eventually, and in the limit, and you get just a polynomial ring as the cohomology ring of this infinite flag variety. And that's the trick here. This implies that there is some unique Schubert polynomial in this polynomial ring in infinitely many variables, which represents every Schubert class compatibly with respect to these maps. And I'll show you again what that means. So there's this notion of stability, which I'll revisit a little bit later. So what is that polynomial? This is kind of like Tom's question. And kind of remarkably, it took until 1982 for Lascaux and Schutzenberger who were both, well, they're sort of combinatorialists by training or by nature. And they described these polynomials. And they initiated the investigation of all of their amazing properties. And I want to tell you about some of them in the kind of 17 minutes or so that remain. First of all, let me tell you how you built these polynomials. So this goes back to 40 years ago almost. So the construction's inductive. You start by writing down the longest permutation. That's the permutation that flips all the elements, n minus 1 all the way down to 1. And I'm just going to define by fiat the Schubert polynomial for that permutation is this polynomial. It's just a monomial, x1 to the n minus 1, x2 to the n minus 2, all the way down to xn minus 1. I wasn't able to write it here, but you see this has a degree n choose 2, which is the dimension of the flag variety. Which is as it should be. And then the inductive step is, well, if your simple transposition, so if you have a permutation and you, the kth and the k plus first parts of the permutation are out of order, then you can put them in order by multiplying on the right by a simple transposition. This is the one that flips k and k plus 1. And that will decrease length in the sense of Coxeter length. So this is a Coxeter group thing. Then you declare that the Schubert polynomial for that permutation, the smaller one, is equal to this operator del k on the bigger one. And this is the biggest one that there is, so that will kind of inductively define all of them. So I'll show you how that works. So this operator is a fairly simple operator. This one does go back to Newton. Newton used this in interpolation formulas. What does it do to a polynomial? It takes the polynomial, you subtract off what you get by swapping the variables k and k plus 1, and then you divide by the difference between xk and k plus 1. Okay, so that's going to be a polynomial because, well, this divides the top. So let's see an example here for n equals 3. I've kind of included some side remarks, but we'll get there. So for n equals 3, for the longest one is 3, 2, 1. That's the opposite permutation. And I'm supposed to write x1 squared, x2. That's just the normalization. If I hit that with this operator del 1, it turns out you get x1, x2. You can figure out from that formula that that's what's supposed to happen. You do enough of these and you get pretty used to it. And on the other hand, if I swap the first two entries, I get 2, 3, 1. And that's supposed to be the polynomial for 2, 3, 1. So it should be x1, x2. And I could do s2 times it, so that would, or del 2 times it, and that would be swapping the entries, the last two entries. So I get 3, 1, 2, and the polynomial for that is x1 squared. And you go on down and you see that if you do del 1, del 2, del 1 again, you get 1. And if you do it in the opposite order, del 2, del 1, and that was supposed to be del 2 there, got left off, sorry. You also get 1. And what's being manifested here is the braid relation for the symmetric group. S2 times S1 times S2 is equal to S1 times S2 times S1. And that's a part of a general phenomenon, which is that the action of these operators on this cohomology ring is a representation of what's called the Nilhaka algebra. So again, that's some kind of Lie theoretic combinatorics. It's some algebra that you build out of a Coxeter group or a Weil group. And these operators are the ones that were kind of, they were studied for general G mod B by BGG and Demesure in the 70s. And the key thing that Lascaux and Schützenberger just noticed, and at the time it may not have seemed like such a big deal, but the right choice for W naught determines everything else in a nice way. If you choose a different polynomial to start with, of course, you'll get different polynomials down here. And it turns out that these have really amazing properties. So here are some of them. The first one is that this polynomial represents the Schubert class, as it's supposed to do, in the cohomology of the flag variety, but independently of n. And that's the key property here. It's stable in the sense that if I do an embedding of this flag variety in a bigger one, well, I can think about that Schubert class in the bigger flag variety, and it'll be the same polynomial that represents it. And what do I mean in terms of W? Well, I could think of it as in n equals 3 as 2, 3, 1, or in n equals 4, you see I'm leaving 4 in the same position, or in n equals 5, 4 and 5 are left in the same position, and so forth. So it sort of doesn't depend on n. Okay, that's sort of a defining property. The other remarkable property is that these polynomials all have non-negative integer coefficients. I'm going to scroll back up and show you here. Sure enough, in that example, there's only 6 of them, but they all have non-negative integer coefficients. And I'll scroll up just a little bit more. From the definition of these operators, there's lots of minus signs. There's no reason that they should have non-negative coefficients. And if you choose a different starting point, they won't. So this is really an amazing property. And anytime a combinatorialist sees non-negative coefficients, we want to know what the meaning is. And there are interesting interpretations of those coefficients in terms of reduced words and combinatorial gadgets. In the case where W is a Grassmannian permutation, so that means that the Schubert variety comes by projection to an ordinary Grassmannian, then this Schubert polynomial equals a Schur polynomial, which is another classical combinatorial thing. It has connections to Lie theory as well. And if W is a vexillary permutation, which I won't talk about much more, but this is a generalization of Grassmannian, and there's a generalization of Schur polynomials, which also have some determinantal formulas. You can write down a determinant for in terms of elementary symmetric functions, and you get a formula, a very explicit formula for these polynomials. And so there's many more properties that I don't have time to go into, but because of all these amazing properties, in the 80s and 90s, people started asking, well, what about other classical groups? Can you find Schubert polynomials for, say, for the symplectic group that have all these amazing properties? So let's look at type C and see what the flag variety is. So in this case, the flag variety is all chains of subspaces. And I've indexed them backwards here. You see the dimension is kind of going down instead of up, but that's okay. It's just an indexing thing. Where the biggest one is Lagrangian. So this one is going to be n-dimensional, sitting in this 2n-dimensional symplectic vector space. And so therefore all the subspaces will also be isotropic. So this is the set of all of these types of flags. And you can define the same kind of Schubert variety as before. I'm not going to tell you exactly what it looks like. There's a similar way of writing down the rank of a Weil group element. Oh, yeah. Is there a question? I cannot see.
No.
So.
Nope.
Oh, okay. I thought I heard something. Yeah, unfortunately, I can't see you. Okay. Yeah, so the Weil group here is signed permutations. That's basically where you just put a plus or minus on each entry of a permutation. And there's some way of writing down a Schubert polynomial, a Schubert variety that looks like this in terms of intersections. So you can think about embedding these flag varieties one in another. And there is a good way to do it and a not so good way to do it. And in the early 90s, Fomin and Kirillov proved that if you do it in the not so good way, embedding one of these flag varieties in the next, then there are no Schubert polynomials in the polynomial ring that represent every single one of these Schubert classes independent of n. But around the same time, Billy and Heyman said, well, there's actually a unique Schubert polynomial in some other ring. And I'll probably just, I'll mention what this ring is on the next slide. But you want to use a little bit of a better stability notion coming from a better way of embedding one of these flag varieties in the next. Okay, so let me tell you about Billy and Heyman's construction, and then we'll kind of take that back to the future. So Billy and Heyman, I'm giving a sort of my own reinterpretation of what they did, but this is essentially what they did. They looked at a system of embedding of Lagrangian Grassmannians, where you embed C2n in C2n plus 2, and so forth, all the way up to some infinite dimensional symplectic vector space. And there's kind of a canonical way to take a Lagrangian subspace and then put it in a bigger Lagrangian subspace. One thing to think about though here is a Lagrangian subspace here is going to be n-dimensional. Here it's going to be n plus 1 dimensional. And eventually your union of all of them is going to be infinite dimensional subspaces of some infinite dimensional symplectic space. So it's a little bit complicated to think about in terms of algebraic geometry. Everything is very infinite dimensional here. But nonetheless, you can compute its cohomology ring. And its cohomology ring is this thing that I'm calling gamma. It has a presentation in terms of Chern classes. The Chern classes are coming from tautological bundles, universal tautological bundles on the Lagrangian Grassmannians. And there's some universal relations among these which basically say they come from Lagrangian subspaces. And here's what they are. I don't expect you to remember them, but they're not too complicated. That's what they are. For every p, there's one of these relations. There's a similar way of constructing flags. So if you project onto the top dimensional piece, the Lagrangian piece of your flag, you get a flag bundle, a regular type A flag bundle. And you can parlay that into a computation which says that the cohomology ring of this infinite flag variety is just take your coefficients in this funny ring, gamma, and take polynomials over that. Okay, and so Billy and Heyman essentially realized this, and they defined a Schubert polynomial to be the element of this cohomology ring, which represents a Schubert class in this stable sense. But what they really did is they gave a formula. They gave a bunch of formulas for these things. And their formulas involved, again, Lie theoretic combinatorics having to do with reduced words which express each W in terms of simple transpositions as a product of simple transpositions. Okay, so this is in the 1994, this is when their paper came out. So a lot of progress has been made since then. Notably, equivariant or in other words, double versions of these polynomials came out. So one thinks of the Y's here as equivariant variables with respect to a torus action. So this is around 2010. Ikeda, Mihalcha, and Uruse wrote down those. The analog, so if you look at Grassmannian elements or Vexillary elements, in the type A version, you had Schur polynomials or determinants, and the analog in this context are Pfaffians, or what's called theta polynomials. And so Buchresch and Tabakis gave a bunch of formulas. They kind of developed this theta polynomial formalism. And together with Fulton, I refined some of these to find some kind of simpler proofs and general, kind of more general formulas. There's applications to degeneracy loci. We saw one at the beginning. I'm not giving the precise translation, but if you take the formulas that one has here, you can then apply it to get that the solution to that quadrix problem. And so these are some of the people involved in that, and there's been a lot more. Okay, in the last few minutes, oh, by the way, yeah, so there are analogs in types B and D. In the last few minutes, I want to go back to type A and talk about recent progress and kind of what's going to happen in the future. So a few years ago, Lam, Lee, and Shimizono realized there's actually a type A analog of these type C, B, and D polynomials. And the idea is you should do the same kind of trick with the Grassmannian as you did for the Lagrangian Grassmannian. If one does this, you compute that the cohomology ring is canonically identified with the ring of symmetric functions. And that has a basis of Schur functions, so they're appearing here again. And then the cohomology of the flag variety will be some polynomial ring with infinitely many variables indexed by the integers, so there'll be negative variables too. With coefficients now not in the integers, but in this ring of symmetric functions. So likewise, Schubert varieties are going to be indexed by permutations of the integers now. And you get what Fulton and I are calling enriched Schubert polynomials living in this big polynomial ring. They represent these Schubert classes, and they form a basis for this big polynomial ring. And these folks, Lam, Lee, and Shimizono, they gave nice formulas, just amazing formulas for them in terms of combinatorial gadgets called bumpless pipe dreams. And Bill Fulton and I have a variation on that, and I want to just kind of almost close with just a picture of what they look like, just to maybe whet your appetite for seeing more of it or not. Here's the formula. You want to express one of these enriched Schubert polynomials as a sum with coefficients of coefficients multiplying Schur polynomials, because we know they form a basis for lambda. So the trick is to say what this coefficient is, and I'll just give it to you kind of by example. So this here is what you do to compute S231. And you can tell that it's 231 because I wrote 2, 3, 1, and I'm connecting. So this is all in order, and this is according to the permutation down the column. And I'm connecting by pipes, 2 to 2, 1 to 1, 3 to 3, 0 to 0, and so forth. And what I do is I record a variable each time I see something in that row. So this is x1 times x2. This one's going to be x2 times a frozen variable, which is that Schubert polynomial. This is going to be x1 times that frozen variable, and then this is this Schubert polynomial up here. And if you looked back at the slides from before, this was the classical Schubert polynomial for that same permutation, 2, 3, 1. So the constant term there is that. And I'm basically out of time, but I wanted to mention some further directions, which are to look at the H-space structure of this infinite Grassmannian, and particularly the new features that one sees equivariantly. And I'll just include with, so even more, you can ask about the affine Grassmannian, which embeds in this infinite Grassmannian. It is homotopic to a loop space of SUN. And you can ask, what are the Schubert polynomials for the affine Grassmannian? And Thomas Lamb really kind of started off this subject a dozen years ago or so. And Lee and all three of these guys have developed it, but there's definitely a lot more to do in this affine setting. It's somewhat harder, but very interesting. So thanks for listening, and that's what I have to tell you.
Nice. Let's thank Professor David Anders. And then we have questions or comments. Someone? Leonardo?
Okay. Hi, David. Thank you for this very nice talk. And going back to the big picture on page 5, what can be said about the real case?
Oh yeah,
I
know you're very interested in that, and I've left that out almost completely here. But that's very interesting too, and that's a whole other connection between Lie theory and transformation groups. You know, I don't know very much kind of the classical algebraic geometry that's been kind of that has exploited that. Some people in tropical geometry kind of can apply tropical techniques to real flag manifolds and real Schubert polynomials, or sorry, real Schubert varieties. But yeah, there's a lot to be done there as well. Now, if you use, for example, if you use Z mod 2 coefficients, then everything turns out to be basically the same. So these formulas I've written down, I guess I didn't say explicitly, but all the variables, you interpret them as Chern classes. If you replace Chern classes with Stiefel-Whitney classes and use Z mod 2 coefficients, then basically everything kind of works out the same. But it'd be very interesting to do things with Z coefficients, for example.
Yeah.
I don't know much more about that, but it's interesting.
Okay, and okay, thank you. And about the exceptional groups, and there is some analogs in this direction.
Yeah, that's a good question. So I was trying to emphasize stability, and so the point is that these flag varieties all come in some series. And stability characterizes these Schubert polynomials, because when you take a limit, you just get a polynomial ring. So the question I would throw back to people asking about exceptional groups, which is very natural to do, is what kind of stability would you like to require? You know, you could take, for example, the E series and try to extend it out. You know, you got E6, 7, 8, but you could keep going to E9 and so forth, and ask about stability in that context. I don't know what, I mean, eventually you run out of geometry, but you can still write down algebra. I don't know what the cohomology ring you would get in the limit, what it would look like, but yeah, that would be something interesting that, as far as I know, no one has worked out.
Okay, thank you, Dave.
Thanks for the questions.
No, nice. That bumpless pipe dreams, right? At the end, you.
Oh yeah.
What's the difference from the pipe dreams?
Yeah. Okay. So if you know about pipe dreams, there's another. I wish I could use my pencil. There's another way of drawing these diagrams. Let me see. Maybe if I. Okay, this will be okay. If I draw something. May not work out so well, but can you see that?
Yeah.
There's another thing that is allowed in pipe dreams. Is you can stick in one of these tiles. This is what they call a bump. And you'll notice that in all of these diagrams, that tile doesn't show up. That's
okay.
what it means to be bumpless. But you're right. Otherwise, there is a similar notion of pipe dreams, and they give another formula. And you know, there's not an easy bijection between these guys and the pipe dream formula for Schubert polynomials.
Okay.
But these ones are the ones that are good for these. So the pipe dreams are good for just the classical Schubert polynomials, which is this leading term here. So if you do pipe dreams, you'll kind of get that. Yeah. But the bumpless ones will give you the extra stuff too. In a good way.
Nice. Got it.
Yeah, it's very beautiful combinatorics that they developed.
Yeah, sure.
And there is the analog to types B, C, and D for these bumpless diagrams.
Sort of. So a few people have written down candidates. I don't think we're at the. I think everybody agrees. Everybody that's working on this agrees that these are the right ones for type A. These have all kinds of wonderful properties. For types B, C, D, a few have been proposed, and I don't think that we're in a settled position. So I would say there's still work to be done in that area. Yeah.
Oh, nice.
Nice.
Yeah.
Okay. Anyone? Lucas? Okay, I think that's so. Let us thank Dave Anderson again